Chapter 16.7 is one of the last chapters in the books, so congratulations for making it so far into this course. And we're going to be looking at an idea called Stokes Theorem. And you're going to see that it really brings together a lot of the ideas that we've talked about all throughout chapter 16, all the way from Green's theorem to surface integrals to finding circulation. All those ideas are really going to come together in this pretty impressive theorem that we call Stokes Theorem. And so I just want to jump in by looking at exactly what the theorem states. We can break down the pieces and then look at an application of it in solving one of the problems. So if we just take a look at Stokes' theorem right here, this is what it says. So here on the left-hand side, what we have is, this should be very familiar. This is a line integral, right? So we're looking here at a line integral of a vector field, right? So we're doing a line integral through a vector field. And you remember, when we do line integrals through vector fields, if that field is, so in general, you're finding the circulation. So this is finding circulation of f on the curve, right? So you have some curve C, your path of integration, going through a vector field, and then by doing that line integral, you're finding the circulation. And then if f is a force, so if f is a force, then the interpretation of that line integral would be the work done. So that gives you work done on C. Right, so that's kind of a review of line integrals. Also, if you notice here, we're doing line integrals where C must be a simply connected path, right? That's what that circle on the integral symbol means, is that C must be simply connected. So this is only applying to line integrals through vector fields, so where C is connected. Okay, so that's the left-hand side. So really you're finding that circulation of f. And what Stokes' theorem says is that the line integral of a vector field that is simply connected is equal to the surface integral. So an integral over a surface, which we just looked at, of this integrand, d sigma. And this is just the surface integral operator, right? So this is the surface differential. So that's just across the surface. So it's saying it's equal to a surface integral where C, the line integral path, is the boundary of the surface on this right-hand side. So S has the boundary C. So this path that you take here, the line integral, is equal to a surface integral over the surface enclosed by C, right? And so now we just need to dissect the integrand of the right-hand side. And so this operator right here, let me choose a different color real quick. So this, the del operator crossed with f, that's called the curl of a vector field. So del cross f is curl. And we'll take a look more at what that means in a second, but that term is curl, and then of course dotted within is just the normal to the surface. It's the normal vector to S. So that's all we're looking at. So I think it would help to take a look at a picture real quick, just to make it a little bit more clear. So here we have a surface. Let me put some axes on it just so we can place it in space. So maybe if we just had some coordinate axes here. So here we have a surface in R3. There's a vector field in that space as well, and that's the red vectors f. And then we have the boundary of the surface. Let me pick a different flavor real quick. So here's the boundary of our surface. And so the boundary is a simply connected curve, right, that we could call C. And so what Stokes' theorem is saying is that the line integral across the boundary of this surface, so the line integral along this curve, is equal to the surface integral, so the integral across this surface of the curl of the vector field. So let me just say that one more time. So the line integral across the boundary of the vector field is equal to the surface integral of the curl of the vector field. So that's all that Stokes' theorem is saying. And so if you're trying to find the line integral of some curve, sometimes it might be easier to instead evaluate a simpler surface integral across the surface that is enclosed by C. Now, an interesting property of Stokes' theorem is that it works for any surface enclosed by C. So this curve here really can enclose infinitely many surfaces, right? One possible surface is the one that's drawn here. Another equally valid surface is just the plane that intersects that entire curve, right? So it could be a flat surface. That's a possible S. So you could use that as the surface for the right-hand side of the equation. You could also use a surface that like balloons out here, right, where it's all of its boundaries are C. That's an equally valid surface as well. So Stokes' theorem really gives us the freedom to choose the simplest surface that can be enclosed with that curve as its boundary. And oftentimes the easiest surface is just the flat plane that goes through the entire curve, the boundary curve. So I mentioned on this right-hand side, you're really doing a surface integral of the curl of the vector field. So I want to spend a second here talking about what the curl of a field really is. So I know we've talked a lot about circulation. So circulation, just as a recall, circulation is like the macroscopic tendency for things to move in a circular pattern. So circulation is global movement in a circle. Oops. So you could imagine that if you dropped a beach ball into a whirlpool, then the tendency for that beach ball to kind of float around in a circular pattern in the whirlpool would be the circulation of that vector field. And now the curl, so curl is like very tiny microscopic circulation that appears everywhere in the vector field. So curl is local, kind of like local circulation. And going with the same beach ball analogy, the curl of a vector field, given that the field might be the movement of that water, would be the tendency for the water to cause the beach ball to spin on its own axis. So you can imagine if I were to just draw a beach ball here real quick. So if you had a beach ball here in the water, then circulation is the tendency for the ball to kind of move in that vector field, or for the vector field to act on the ball so that it moves in kind of this type of pattern. Whereas curl would be how much the vector field is actually causing the ball to spin on its own axis as it moves. So this type of movement is described by the curl of the vector field. So let me just get rid of this for a second. And the way we find curl, so the curl of F is equal to the del operator crossed with the vector field. And of course, you know, the way we evaluate a cross product is the determinant of that 3x3 matrix where you have I, J, and K up here. And then the del operator, remember, is that set of three partial derivatives in the respective directions. So we'll have the partial with respect to x, partial y, and partial z. Right? Those are partials, not 2's. Let me make those a little bit more clear. So it's the partial, partial, partial. And then down here, you would have the components of the vector field f. So you would have the x component. Let me find a way to write that. So if f is p, q, and r, then down here you would put those respective components. And so the evaluation of that gives you the curl of f at every point in the vector field. So how much the vector field at every point is causing that local rotation. Okay, so let's take these ideas and apply it to one problem. We're only going to do one example today because these problems can get very long and very tedious with the calculations. But I think doing one good representative example will give you enough insight to take this and do some more on your own. So let's use Stokes' theorem to calculate the circulation of this vector field around a curve C. So if you look, the wording of the question is almost identical to everything we described up here on the right hand or the left hand side of Stokes' theorem, right? So we're finding the circulation of the vector field on some curve. So it presented us with finding this, right? But it tells us to use Stokes' theorem. So we're really asking to use the equivalent surface integral that is really the key point in Stokes' theorem. So here we go. We have over here, here's our vector field. Here's our vector field F. And then C is the boundary of the triangle cut from the plane x plus y plus z equals 1 in only the first octant where we traverse it counterclockwise when viewed from above. So let's just sketch what our path of integration even looks like. So over here we're just going to sketch C. So let me get some axes like this. Okay, we know the plane x plus y plus z equals 1 is just going to be that plane kind of situated at a 45-degree angle, right? When x is 0, you have the line y plus z equals 1, which gives you intersections at 1 on all the axes. So you get this plane, oops, right here. And then, so this is our curve C. And then we want to do the line integral traversing it counterclockwise from above. So that means, let me think, from above, we're going this direction. So all we're doing is we're finding that circulation on that path where this vector field is kind of permeating this space. So there's vectors all through there, and we want to find that circulation. Let's apply Stokes' theorem. And so instead of doing the line integral across that path, we're instead going to do a surface integral, right? A surface integral of where the integrand is the curl of the vector field. So the first thing we need to do is pick a surface. And right, remember I said that the surface you pick to do the surface integral of can be any surface whose boundary is that curve. So we could pick a big ballooned out surface, right? We could find some equation that gave you kind of this, if you could imagine it as some like kind of triangular bubble. That's a possible surface. But like I mentioned earlier, oftentimes the easiest surface to pick is just the plane that lies in the plane created by your curve. So really S that we're going to pick is just the plane x plus y plus z equals 1. So we're going to use this as the surface to do the surface integral on. Okay, fantastic. So the first thing we need to do is, let's just rewrite Stokes' theorem real quick, just to have it in front of us to use. So just as a reminder. So a reminder. Stokes' theorem is the line integral across a curve of the vector field is equal to the surface integral of the curl, right, dotted with the normal vector, ds. And if you remember, to turn this into a more usable form, from the last section on surface integrals, this integrand can be expanded to be the surface integral. Remember, anytime we do a surface integral of a vector field, it just becomes that vector field times the cross product of the two partial derivatives of the parameterization of the surface, dx dy. Right, so that's the usable form. And in this case, we're just going to treat the curl field as the field that we're doing the surface integral on. So once we evaluate the the field that we get after doing the curl, we'll just treat that as if it was f. You'll see how that works here in a second. So really, the usable form of the right-hand side of the equation is the curl. Right, we're just going to dot that with our x. Well, I guess we haven't picked our parameters yet, so I'll just do u's and v's for generic ones. Right, then we have du, dv. So that's straight from the last section on evaluating surface integrals. That's the usable version in terms of our parameter. So I guess the first thing we'll do is, just to get started, is I'll parameterize the surface we chose. So let's take a second to parameterize our surface. So we need to pick two variables to parameterize with. I'm just going to pick x and y. And because the surface we're parameterizing is just x plus y plus z equals 1, I'm just going to make z be like the dependent variable, and we can rewrite that as z equals 1 minus x minus y, and plug that into our parameterization. So in this case, we'll just get x in the I direction and y in the j direction, because those are our parameters, and then we have plus 1 minus x minus y for the z component. So there's the parameterization of this surface we chose. Now the next thing we need to do is, why don't we calculate the curl of f? So now we're going to work on finding this term in the integrand, curl f. Let me pick a new color for this. So let's find curl of f. And where we remember that's equal to this crossed f, which in this case is going to be I, j, k, with partial x, partial y, partial z, and then what are the components of our vector field? It's y, x, z, and x squared. So let's evaluate this matrix real quick. We'll get, for the I component, we'll have the partial y of x squared, which is 0, minus partial z of xz, which is just x. So we will end up having the minus x, right, because it's this minus that. So we'll end up with minus x in the I direction. And now we have, right, minus, due to cofactor expansion when we're evaluating this matrix. Partial x of x squared is going to be 2x minus partial z of y, which is 0, so we'll have minus 2x in the j direction. And then we have plus the last component, which is going to be partial x of xz, which is just z minus 1. So now we have, for this last component, we get z minus 1 in the k direction. Okay, so we calculated this term in the integrand. Now let's work on doing the second factor, which is the cross product of the two partial derivatives of our parameterized surface. So now let me pick another color to do this part in. So now we need to find our x crossed with our y. So in this case, our surface partial derivative in the x with respect to x, in this case, is going to be 1i, so we get I, plus 0j minus 1k, so we get I minus k. Now we'll do in the y direction, we'll get 0i, 1j, again minus a k. And now we'll do the cross product of those two. So we'll get our x crossed with our y. In this case, we'll do another matrix. In this case, we'll have 1, 0, negative 1, and then 0, 1, negative 1. And then just to save some time, I already know this is going to come out to be 1i plus 1j plus 1k. Because I solved this problem beforehand. Okay, cool. So now we have this second factor in the integrand. And if we want to, now we can dot them together. So we're going to do now the dot product of this curl and of this vector. And so because this second vector is just 1, 1, 1, when you dot them together, you're really just summing the coefficients of this vector right here. Right, so over here real quick, let's just do, so this dotted with this, right, which are, again, this vector in this vector, is going to come out to be negative x minus 2x plus z minus 1. Now we can simplify that to be minus 3x plus z minus 1. Okay, fantastic. So this is going to be the entire integrand of our surface integral. So let's start actually writing our surface integral put together. So in this case, we'll now put our surface integral here over a surface where the integrand is minus 3x plus z minus 1 dy dx. Now remember, because our variables of integration, because of our parameterization, are x and y, we need all the variables in the integrand to also be x's and y's. So we need to get rid of this z, but thankfully we have an equation that relates z to our parameters, right? Z is equal to 1 minus x minus y. So I'm just going to plug in that for our parameterization. So I'll plug in z equals 1 minus x minus y, so that we're using all the correct variables. So that will become the double integral of minus 3x plus 1 minus x minus y minus 1. And let's simplify that here for a second. So the 1's will cancel out. You'll have minus 4x minus y. So this comes to negative 4x minus y. dy dx. Great. So the last thing we need to do to evaluate this surface integral is to bound the surface in terms of our parameters. Right, so our parameters, remember, are x and y. So we need to find x and y bounds of this surface. So luckily, because our variables are x and y, the bounds are going to be on the xy plane. And the bounds are just going to form, right, this, let me pick a different size. Right, so we're looking to bound on the xy plane. So here we go. And of course, we can rewrite this boundary equation as, right, this curved line right here can be written as 1, or y is equal to 1 minus x. Yep, that gives us that. So if we go in the y direction first, we'll just go from y equals 0 to y equals 1 minus x. And then in the x direction, we'll just go from 0 to 1. So that's pretty easy. So let me plug those in here. So we'll get from y equals 0 to y equals 1 minus x, and then from x equals 0 to x equals 1. And let me just put some brackets around here so it's all grouped together. Okay, fantastic. So let's just evaluate this integral now. So now we're going to get, that is equal to the integral from 0 to 1 of, let's see, with respect to y, we're going to get negative 4xy minus 1/2 x squared, or y squared. Yes. Evaluated from 0 to 1 minus x dx. So now we'll plug in the 1 minus x into all of our y's, and we'll get from 0 to 1 of negative. I'll put a big bracket here. What do we get? Negative 4x times 1 minus x plus 1/2 1 minus x squared dx. And now we just have one final integral that we can use power rule on, and that will all come out to be negative 5/6. So that's the final answer. And so just to recap what we did with this problem, it's very long, but we used Stokes Theorem to convert doing a line integral around the boundary of some curve, a line integral across some curve, right? We instead use Stokes Theorem to do a surface integral over the surface contained within the boundary of the path of integration. And the thing we did the integral on was the curl of the vector field, which is how much that vector field is causing that very local rotation motion.